Scientists may have found a signal that connects two of the biggest mysteries in physics. I want to explain exactly what that means. No hype, just what we know, what we don't, and why this matters. Let me start simple. There are particles called neutrinos. They have almost no mass. They carry no electric charge, and they interact with almost nothing. Right now, billions of them are passing through your body. Every second. You don't feel it. They don't care. They pass through you the same way light passes through glass, except even easier. A neutrino can travel through a full light year of solid lead without hitting anything. A light year of solid lead, and still come out the other side. That's how ghost-like these things are. Scientists actually call them ghost particles, and honestly, that name fits. Now here's the second mystery: dark matter. This is stuff we've never directly detected. We can't see it. We can't touch it. We have no idea what it's made of. But we know it's there. The way I understand it, we know it's there because of gravity. The gravity we can measure in the universe doesn't match the matter we can see. Galaxies spin too fast. Light bends more than it should around certain objects. There's extra gravitational pull coming from somewhere. Something is causing it. That something is what we call dark matter. The current theory says it makes up about 27% of everything in the universe. Regular matter, you, me, stars, planets, every atom we've ever studied, that's only about 5%. Dark matter outweighs everything we've ever seen by a massive amount. So we have these two things: neutrinos, which are real but nearly undetectable, and dark matter, which is real but completely undetected. Both are mysterious. Both are hard to study. Both are fundamental to how the universe works. Now, in January 2026, a paper was published in Nature Astronomy. The researchers, Zhu, Jiare, Zhang, and others, did something interesting. They didn't just look at one type of data. They combined multiple different measurements of the universe. They looked at how matter is spread across space. They looked at the cosmic microwave background. That's the faint glow of light left over from the very early universe, like the afterglow of the Big Bang. They looked at galaxy surveys. They combined all of this and asked, does the data fit better if neutrinos and dark matter interact with each other? And the answer they got was, yes. The data fits better if they do. That's the signal, a 3 sigma signal. I want to explain what that number means because it matters a lot. In physics, a sigma is a way of measuring how surprising a result is, how far it sits from what you'd expect by random chance. A 1 sigma result could easily be a fluke. 2 sigma is more interesting, but still might be nothing. 3 sigma means the chance of this result being random noise is about 1 in 370. That sounds impressive. And it is interesting. But in physics, 3 sigma is not a discovery. Discovery requires 5 sigma. The difference is huge. At 5 sigma, the chance of random noise is about 1 in 3.5 million. 3 sigma results have appeared before and later turned out to be nothing. The researchers themselves say this clearly in the paper. This is a signal. It needs confirmation. It is not a confirmed discovery. To me, that honesty is actually what makes this paper credible. They're not claiming more than the data shows. So what exactly is the interaction they're talking about? The idea is that neutrinos, which are normally supposed to pass through everything without interacting, might actually have a very small, very weak interaction with dark matter particles. Not strong, not obvious, but just enough to leave a tiny mark on the large-scale structure of the universe, like a whisper instead of a shout. And when you compare the patterns in the universe's matter distribution to models that include this interaction versus models that don't, the ones that include it seem to fit the data slightly better. Now here's where it gets even more interesting to me. This isn't just random. There's actually a reason to look for this interaction. It connects to a known problem in cosmology called the S8 tension. The S8 tension sounds technical, but the idea is simple. We have two different ways of measuring how clumpy matter is in the universe. One way uses the cosmic microwave background, that ancient light from the early universe, to predict what the distribution of matter should look like today. The other way actually looks at the matter distribution today, using galaxy surveys and a technique called weak gravitational lensing, which is basically measuring how light gets bent by mass. When you compare the two measurements, they don't quite agree. The universe today looks slightly smoother, less lumpy, than the early universe data predicts it should be. That disagreement is the S8 tension, and it's been bothering cosmologists for years. The way I see it, this is a genuine problem. Both measurements are done carefully. Both use well-established methods, but they give different answers. That kind of disagreement usually means one of two things. Either there's a systematic error somewhere, something in the measurement process that we're not accounting for, or there's new physics, something our current models are missing. The neutrino-dark matter interaction idea is interesting precisely because it could explain the S8 tension. Here's the logic. If neutrinos interact slightly with dark matter, it would slow down how dark matter clumps together in the early universe. Dark matter clumping is what drives the growth of large-scale structure, galaxies, galaxy clusters, all the big shapes in the universe. If something slows that clumping down, the universe ends up a bit smoother, which is exactly what the observations seem to show. So this proposed interaction could actually resolve a known disagreement between two sets of real data. That's not nothing. That's genuinely important if it holds up. But again, if. That word is doing a lot of work here. Now let me add the second piece of this, because there's another result from a completely different experiment that adds more context. In December 2025, about a month before the Nature Astronomy paper, the Lux-Zeppelin experiment, also called LZ, published results from its largest dataset yet. LZ is a dark matter detector. It's located about a mile underground in a mine in South Dakota. The reason it's underground is to block out cosmic rays and other background radiation. You want to eliminate as much noise as possible when you're trying to detect something as rare as dark matter. The detector itself is a tank containing about 10 tons of liquid xenon. The idea is that if a dark matter particle passes through the xenon and bumps into a xenon atom, it should produce a tiny flash of light. You detect the flash. That's your signal. LZ is one of the most sensitive dark matter detectors ever built, and the December 2025 results were significant in two ways. First, the experiment didn't find dark matter, but that finding is still useful. Every time a detector like this runs without finding anything, it narrows down what dark matter can possibly be. It rules out certain types of particles with certain masses and certain interaction strengths. Each null result, each non-detection, tightens the allowed space of what dark matter could be. Scientists call this setting new limits, and LZ set the tightest limits yet for certain types of dark matter candidates. Second, and this is what really surprised me when I read about it, LZ detected solar neutrinos using a process that had never been seen in an experiment before. Solar neutrinos are neutrinos coming from the sun. The sun produces enormous numbers of them through nuclear reactions in its core. And LZ picked up a specific type of interaction, neutrinos scattering off electrons in the xenon, through what's called coherent elastic neutrino nucleus scattering, a process that was only theoretically predicted for a long time. Detecting neutrinos was almost a side discovery. LZ wasn't primarily built to detect neutrinos, but it did. And that detection tells us the detector is working at an extraordinary level of sensitivity. If it can pick up neutrino signals it wasn't designed for, that tells you something about how precisely it's measuring the quantum world. What I find interesting is that these two results, the Nature Astronomy paper and the LZ results, don't come from the same team or the same experiment, but they're both pointing attention at neutrinos and dark matter at the same time. That's not a coincidence in terms of timing. It's more that both fields are now sensitive enough to probe these questions. The tools caught up. That's what makes 2025 to 2026 feel like a turning point in this research. Let me take a step back and explain why the idea of neutrinos interacting with dark matter is strange at all. Because it requires understanding what we currently think about both. In the standard model of particle physics, the best description we have of how particles work, neutrinos interact through only two of the four fundamental forces: gravity and the weak nuclear force. They don't interact through electromagnetism. They don't interact through the strong nuclear force. That's already why they're so hard to detect. They barely interact with anything. Dark matter, as far as we can tell, also doesn't interact through electromagnetism or the strong force. That's why it's dark. It doesn't emit or absorb light. It interacts through gravity, and possibly through the weak force, and possibly through some force we haven't discovered yet. So the idea of neutrinos and dark matter interacting is not completely impossible within physics. They could potentially interact through the weak force. Or there could be some new mediator particle we don't know about yet, something that bridges these two otherwise ghost-like particles. The Nature Astronomy paper doesn't specify exactly what the interaction mechanism would be. It just looks at whether the data fits a model that includes some interaction. And it says, yes, slightly better. The researchers describe the result as pointing toward what they call a fundamental breakthrough in cosmology and particle physics. But that language is conditional. They're describing what it would be if confirmed, not claiming it is confirmed. That's an important distinction. The way I read it, they're being appropriately cautious while also being honest that the implications would be enormous if this holds up. Because think about what it would mean. We'd have evidence that two of the most abundant but least understood types of particles in the universe actually talk to each other. Neutrinos make up a significant fraction of all particles that exist. Dark matter makes up 27% of the entire universe. If they interact, even weakly, that would reshape how we model the universe's formation. It would give us a new tool to detect dark matter indirectly. It would help explain the S8 tension, and it would almost certainly require new physics beyond the standard model. That's enormous. Which is exactly why we need more than a 3 sigma signal before accepting it. Now, what happens next? How do we find out if this is real? The researchers point to future experiments. There are several next-generation surveys either running or launching soon. The Euclid Space Telescope, launched by the European Space Agency, is now mapping the shape and distribution of galaxies across the universe at a level of detail we've never had before. That data will directly help test whether the neutrino-dark matter interaction idea fits. The DESI survey, the Dark Energy Spectroscopic Instrument in Arizona, is also building an enormous map of galaxy positions and how they've moved over time. Both of these will give us much better measurements of the S8 type of data. If the current 3 sigma signal is real, these surveys should push it higher. If it's not real, they should make it go away. There's also the CMBS-4 project, a future telescope array that will measure the cosmic microwave background at much higher precision than we have now. And future runs of LZ and similar detectors like xenonnt in Italy. These experiments will either find the signal getting stronger or getting weaker. That's how science works. You get a hint, you look harder, you either confirm or you move on. I want to address one thing directly. Some people will see this kind of news and think scientists are stringing us along. Another maybe, another we're not sure. I understand that frustration, but the way I see it, this is actually how you know the science is real. When researchers publish a result and immediately say, "This needs confirmation," that's intellectual honesty. It's the opposite of hype. The history of physics is full of 3 sigma signals that went away. It's also full of ones that became real discoveries. You don't get to know which is which until you check more carefully. And we're in the checking phase. What I found genuinely interesting while reading about this is how the 2 experiments reinforce each other without being connected. LZ shows neutrinos can be detected in new ways at high sensitivity. The Nature Astronomy paper shows there's a statistical hint of neutrino-dark matter interaction in cosmological data. One is a direct detector underground. One is pattern analysis of the entire observable universe. They're using completely different methods, and they're both drawing attention to the same 2 types of particles. That kind of convergence, even if neither result is definitive, is the sort of thing that makes physicists pay attention. Let me also say something about dark matter detection in general, because it's worth understanding where we stand. LZ's null result, not finding dark matter, sounds like failure. But it's not. Every non-detection eliminates possibilities. The most popular dark matter candidate for a long time was something called a WIMP, a weakly interacting massive particle. The idea was that dark matter is made of particles with a mass somewhere between a proton and maybe 1,000 times a proton, interacting through the weak force. That was the leading theory for decades. Detectors have now ruled out a huge portion of the WIMP parameter space. LZ's latest results push that further. The original most favored WIMP properties are looking increasingly unlikely. That's not failure. That's the search narrowing. It means if dark matter is a WIMP, it has to be different from the most obvious version, or it's not a WIMP at all. Both options are scientifically important to know. The neutrino interaction idea, interestingly, might work better if dark matter is lighter than the typical WIMP assumption. Some of the theoretical models that include neutrino-dark matter interaction involve what are called light mediator particles, particles that are much lighter than originally assumed in classic WIMP models. This is one of the reasons the 2 threads of research, LZ's constraints and the cosmological signal paper, feel connected even though they're separate experiments. As WIMP models get ruled out, researchers explore new territory, and that new territory includes exotic interactions between neutrinos and dark matter.